Empirical relations for forced convection heat transfer in tube banks. Okay, so this is basically your core blueprint for designing efficient heat exchangers. The goal is always to get the most heat transfer you can while using the least amount of energy possible to pump the fluid through. First up, it all comes down to the physical arrangement of the tubes. You've got two main choices, either an inline pattern or a staggered one. And the spacing is so important here. A tighter, staggered layout? Well, that's going to boost your heat transfer like crazy. But there's a catch. You'll pay for it with way more resistance to the fluid's flow. Second, you absolutely have to figure out the maximum flow velocity. See, as the fluid squeezes between all those tubes, it speeds up a lot. So all your big calculations, especially the Reynolds number, have to use that max velocity, not the slower speed it came in with. Why? Well, because that's where the real action, the critical heat transfer, is actually happening. Third, we rely on empirical correlations. Think of them as proven formulas, like the ones from Zukowskis. These help us find the heat transfer coefficient, which we usually talk about as the Nusselt number. And really, the Nusselt number is just a simple way to score how effective the heat transfer is. And finally, let's talk about the practical side, the pressure drop. This is pretty much the friction loss, and it tells you how big and powerful your pump needs to be. You'll use friction factors and that max velocity to make sure your pump can handle the job without, breaking the bank. Let's dive into more detail.
All right, let's dive into something that's at the absolute heart of chemical engineering, the heat exchanger. You're going to see these everywhere. The real challenge, the thing that separates the pros from the rookies, isn't just knowing what they do. It's being able to predict exactly how they'll perform. It's this awesome mix of physics, math, and what I like to call engineering judgment. So picture this. You're the engineer. Someone hands you a design with a bank of hot tubes and tells you cool air is going to be flowing over them. Your job is to figure out exactly how much heat is going to move from those tubes into the air. This isn't about making a wild guess. It's about following a logical, step-by-step process. And that's exactly what we're going to do together right now. So how are we going to tackle this? Here's our game plan. First, we'll lay out the problem, get all the facts straight. Then, we'll map out the physical geometry of the system, because believe me, in heat transfer, the shape of things is everything. Next, we'll assemble our toolkit of essential formulas. After that, we'll actually plug in the numbers and solve it. And finally, we're going to ask the most important question an engineer can ask: how much should we actually trust our answer? We're zooming in on a really common scenario called a forced convection. All that means is we're using a fan or pump to actively push a fluid, in this case air, across a bundle of tubes to get that heat moving. This concept is the engine behind countless industrial processes. Okay, so what are we working with? Here are the vital stats for our specific problem. The fluid is air, coming in pretty cool at 10 degrees Celsius, and moving at a good clip, 7 meters per second. It's flowing over a bank of tubes that's 5 rows deep, and they're set up in what's called an inline arrangement. And those tubes, they're being held at a constant 65 degrees Celsius. So those are our knowns. Our mission is to find the one big unknown, the total heat transfer rate. Now, before we even think about touching a calculator, we have to understand the physical setup. I can't stress this enough. In heat transfer, the layout, the spacing, the arrangement of all the parts, it's absolutely critical. It completely dictates how the fluid is going to move and behave. You basically got two ways to set these tubes up. You can have an inline arrangement, where each tube sits directly behind the one in front, creating these neat straight lanes for the air to flow through. Or you can have a staggered layout. See how they're offset? This forces the air to take a much more winding, zigzag path, which really mixes things up and can dramatically change how well heat is transferred. For our problem, we're dealing with that straightforward inline arrangement. Now here's a super important concept. That 7 meters per second we started with, that's the speed of the air before it enters the tube bank. But it's not the most important velocity for our calculations. The number we really care about is the maximum velocity, or Umax. This is the speed the air hits when it gets squeezed through those tightest gaps between the tubes. It has to speed up to get through, and that's where the most intense heat transfer really happens. So how do we find that speed? Well, for an inline setup, we have this handy little formula. The maximum velocity, Umax, is just the incoming velocity, U infinity, times a simple ratio based on the geometry. It's the transverse pitch, Sn, that's the center-to-center distance between tubes side by side, divided by that same distance minus the tube's diameter, d. This neat little equation is our key to figuring out just how much that air is forced to accelerate. Okay, we've got the lay of the land. Now it's time to open up our engineer's toolkit and grab the formulas we're going to need. These are the powerful concepts that will let us translate the physical shape of our system into an actual, concrete prediction of how it's going to perform. First up, the big one, the Reynolds number. The best way to think about it is like a weather report for the fluid flow. It's this clever, dimensionless number that basically tells you if the flow is going to be smooth and orderly, that's called laminar, or chaotic and messy, which we call turbulent. And spoiler alert, when it comes to heat transfer, a little bit of chaos is usually a very good thing. Next in our toolkit is the Nusselt number. If the Reynolds number is the weather report, the Nusselt number is the final score. It tells us how effective the heat transfer is. Specifically, it's the ratio of heat getting moved by the flowing fluid, that's convection, compared to how much would move if the fluid were just sitting still, which is conduction. A high Nusselt number means we're doing a great job moving heat. Calculating this is our main goal. So, the million-dollar question, how do we connect the flow weather, the Reynolds number, to the heat transfer score, the Nusselt number? Well, we use something called an empirical correlation. This one here is from a researcher named Grimson. It wasn't just invented from theory, it was built by analyzing data from tons of real-world experiments. It links our Nusselt number, nu, to our Reynolds number, Re, and another property of the fluid called the Prandtl number. Those two other letters, C and N, are just constants that we're about to figure out. So where do these mysterious C and N values come from? We don't just guess. We look them up in a table that's been compiled from experimental data. So for our problem, we know the arrangement is in line. We also know the spacing to diameter ratio is 1.5 in both directions. We just go to the table, find the row and column that match our setup, and boom! The table tells us that for this specific geometry, C is 0.278 and N is 0.620. We've now officially customized this formula just for our problem. All right, we have our mission, we understand the layout, and we've gathered our tools. It's time to put it all together and actually solve this thing. Let's walk through it step by step. This is our roadmap to the final answer. First, we'll get the properties for our air. Second, we'll calculate that all-important maximum velocity. Third, we'll find the Reynolds number. Fourth, we'll use our big correlation to get something called the heat transfer coefficient. Fifth, we'll make a really important correction. And finally, step 6, we'll calculate the total heat transfer. Let's get to it. Step 1 is absolutely foundational. You can't skip it. The properties of air, like its density, its viscosity, they all change with temperature. So which temperature should we use? The incoming air at 10 degrees? The hot tube surface at 65 degrees? Nope. We use something called the film temperature. It's just the simple average of the surface and the air temperatures. So that's 65 plus 10 divided by 2, which gives us 37.5 degrees Celsius. We'll look up all our air properties at that specific temperature. Okay, on to step 2, velocity. We take that formula for Umax we talked about earlier, and we plug in our numbers. With the air coming in at 7 meters per second, the math shows that as it squeezes between the tubes, it accelerates all the way up to 21 meters per second. Whoa! That's a 3-fold increase, and that is the speed that's really driving the heat transfer. Step 3, the Reynolds number. We take our maximum velocity of 21 meters per second, combine it with the tube diameter and the air properties we found at our film temperature, and we get a Reynolds number of 32,020. Now, that number tells us something really important. Because it's so high, well over a few thousand, it confirms that the flow is definitely turbulent. And remember, for heat transfer, turbulent is good. It means lots of mixing. Now for the main event, step 4. We take our Reynolds number, our Prandtl number, and our special constants C and N, and we plug them all into the Grimson correlation. This lets us solve for the Nusselt number, and from there, we can easily calculate H, which is the heat transfer coefficient. We get a value of 164. But, and this is a really big but, that correlation is designed for a deep tube bank, one that's 10 or even more rows deep. And that brings us to step 5, a crucial reality check. Our heat exchanger only has 5 rows. That means the flow doesn't have as much time to become what we call fully developed. The turbulence isn't quite as intense as it would be in a deeper bank, so we have to correct for this. We go back to our trusty lookup tables, and we find that for a 5-row inline bank, we need to apply a correction factor of 0.92. So our real heat transfer will be about 8% lower than that ideal number we just calculated. And here we are, the final step. We take our corrected heat transfer coefficient and we plug it into the overall heat transfer equation. This calculation brings in the total surface area of the tubes and the temperature difference driving the whole process. We run the final numbers, and we get our answer. The total rate of heat transfer is 45.6 kilowatts for every meter of tube length. We did it! So we've got a number, 45.6. We're done, right? Well, not quite. As an engineer, getting a number is only half the job. Now we have to step back and ask a critical question. How good is that number? How much confidence can we really have in this result? To see what I mean, let's try using a different tool from our toolkit. This is another highly respected correlation developed by a researcher named Sukauskas. If we run our exact same problem with the exact same numbers through this second model, look what happens. We get a corrected H value of 186.3. That's way different from the 150.9 we got with the Grimson method. In fact, it's about 23% higher. So which one is the right answer? And this brings us to what might be the single most important lesson today. This quote right here from the textbook says it all. These incredibly useful formulas, they aren't perfect laws of physics like F equals ma. They are brilliant, powerful approximations that were built from real, messy experimental data. And because of that, they have an uncertainty built right in this case about plus or minus 25%. And notice that 23% difference we found? It falls right inside that uncertainty window. This right here is where engineering stops being just math and starts becoming an art. The skill isn't just calculating one number. It's about understanding the limitations of your tools, knowing there's a range of possible outcomes, and using your judgment to design something that's safe and effective anyway. That is the real code Heavecraft today.